All right, good evening, and welcome back for our second presentation in the 2016-17 series of Mercury to Mars. LPI explores the solar system. We're featuring presentations from our scientists here in the building, so get a bit of a chance to see not everything, but what types of things, some of the things that our scientists are researching here at LPI, right, here in our Clear Lake community. Like I said, it's our second talk tonight. Last month, we heard from Paul Spudis talking about the value of the moon, which was pretty interesting, I thought. You may even want to buy his book. I'm not pitching it. I'm just reminding you that he has one. And tonight we'll hear from Dr. Buck Sharpton on this topic. Our next one won't be until February, as you've probably seen from the flyer if you picked it up already. Something about the holidays that get in the way, and then there's this big conference we get to plan for in January. So pretty busy around here the next few months, so come back February 2nd. Groundhog Day. So hopefully it's not the second or third time around for you when you come in. I wouldn't be surprised if George does something to play off on that, but you just have to come and find out. Also, real quick, I want to welcome those of you who may be joining us online. We do now Ustream all our presentations, and we had a good number that were on last time, actually. So if you're joining us again tonight, welcome and thank you for being here. Any teachers in the audience? We have certificates for you at the front desk. Hopefully you grab that. And we now actually did it right, so it should actually work because we put the right number on it. Anybody catch the Pluto news this week? Kind of interesting. All the ice that accumulates on that heart-shaped region over time has actually possibly caused it to move and tilt, which is kind of interesting. So yeah, some news from Paul, and one of our scientists, Paul Schenck, is an author on that paper. You've heard Paul, so if you've heard him, you remember him. If you've seen him, you remember him. That's true too. Thanks, Buck. And also, don't forget, if you're brand new tonight, welcome. And we have a sign-up sheet here by the front door on the black tablecloth. If you want to put your email down, you'll get our emails about this series in the future. And don't forget, of course, there's always a reception in the lobby to follow. But before the food, presentation, and I'll ask Dr. Louise Proctor to come up. Again, Louise is our brand new director here at LPI, and she's going to tell us more about Buck.
Thank you. I don't think I need applause, but thank you. I don't know how long I'm going to keep getting introduced as the new director, but I'm going to milk it for all it's worth. So I was trying to keep this short, but Buck is a very accomplished guy, so I'll keep it as short as I can. But it's my very great pleasure to introduce you to Dr. Buck Sharpton. He's one of our senior scientists here at the LPI. Buck received his PhD and master's degrees in geological sciences from Brown University, and he came to the LPI as a staff scientist soon afterwards. He spent about 12 years here before taking a position as a professor of geophysics at the University of Alaska, a small climate change there, I guess. Mm-hmm. And he stayed at the university for well over a decade, during which time he founded and was the director of the Geographic Information Network of Alaska. He was also the Vice Chancellor for Research, so these are pretty important roles. And in 2008, he was appointed by President Bush to the U.S. Arctic Research Commission, and in 2010, President Obama made him the chair. In this role, he led the development of an integrated Arctic research policy that provides a framework for effectively utilizing the $400 million that the nation spends on Arctic research every year. In 2011, Buck returned to us at LPI and has been here ever since. His plan-show research spans 3 decades and a wide variety of targets and techniques. So these include fieldwork, the use of synthetic aperture radar data, and petrographic microscopy, to name but a few. He's been an author on over 75 papers in subjects ranging from Venusian landforms to the role of impacts in the terrestrial biological record. He was a member of the Magellan mission to Venus, and more recently was the principal investigator of 2 Discovery mission proposals to that same planet. So Buck is one of the foremost experts on the planet, indeed in the universe, on impact cratering, and we're very excited to have him here to speak to us tonight. So ladies and gentlemen, Buck Sharpton.
Thank you, Rose. Before you do that, can you hear me? I think I can hear me, so Wow, I am really impressed. How many people are on the verge of retirement or are retired? Raise your hands. My people. I love it. Yeah. I'll be joining you next year sometime. Now, how many are students? Raise your hands. Students with boundless curiosity and limitless energy, right? And a little arm twisting to come here, maybe? You're my peeps also. Yeah. Thank you, Andy. You can lower those. Thank you very much, Louise, for that introduction, and I want to thank Andy for giving me the opportunity to come here and speak tonight. And thank you all for coming out and showing interest in something other than politics for a change. So, it's just wonderful. What you see here in this cover slide is a picture of the 5 bodies that constitute the inner solar system. And these are all natural color images as you would see them if you were sitting out in space some distance from each planet. The one on your left is Mercury, obviously, then Venus, then the Earth, and down below Earth is Earth's moon, and then Mars out at the far extreme of the inner solar system, just before you get to the asteroid belts. The inner solar system has given us a diverse set of planets on which to investigate the consequences of high-speed collisions between that planet and projectiles such as asteroids and comets. And cratering occurs at all scales, from the microscopic, almost molecular scale, all the way out to the large objects that in the very earliest epoch of the solar system, actually these planetoids or planetesimals came together fairly slowly but with considerable energy and heat to actually build these planets themselves. And toward the end of that era, about 4 to 3.8 billion years ago, we had the remnants of that accretionary period when you had very large basin-forming events. And when you look at the moon, the one down at the bottom of the slide, you can see the large circular features that form the man in the moon. Those are the large impact basins on the near side of the moon that have been subsequently filled with volcanic lavas from about 3.8 to about 2.5 billion years ago. But the interesting thing about it is not just their size, and this slide shows these objects with the same scale. So the Earth is obviously the largest. Venus, just to its left, is about 82% the mass of the Earth. The next largest is Mars, and it's about 11% the mass of Earth. And then Mercury is about 6% of Earth's mass. And then the moon is only a runt. It's only about 1% the mass of the Earth. Now, why is this important? Well, the mass dictates surface gravity. And one of the big constraints on how large a crater will grow is the surface gravity. It retards the motions that generate the crater itself. So there are some factors in the process that cause craters to grow very large, and those would be the velocity of the projectile itself, strangely enough, the angle of the impact event itself, the strength or the lack thereof of the target material, and whether or not there's an atmosphere that the projectile has to transect before it gets to the solid surface of the planet. All of these things have fundamental influences on the final crater form. Let's see now. Before we turn that light off, I should have looked to see. Here we go. All right, so At reasonably small diameters, but still quite large on most planets, you form these bowl-shaped craters. They're called simple craters because their morphology is quite simple compared to the larger scale craters themselves. And you can see in the one on the left, upper left, right here, this is Lunar crater. It's about 2.2 kilometers. It's on the moon, and it has a raised rim that's quite circular in this case. Sometimes they're not so circular. We won't get into too much of that tonight. But the depth is quite deep. It's about 20% of the rim-to-rim diameter. But as the size of the cratering event becomes larger and larger, it reaches a point where the gravitational field of the planet itself begins to exert an influence, and it undergoes a transmogrification, if you will, from the simple form to the complex form. And all three of these craters are complex craters, and you can see they're fundamentally different in their morphology. They have a very complex rim zone here that's scalloped and consists of a number of scarps that are inwardly facing. It has a flat floor, and it has a central structure here. These are called central peak craters. And the depth to diameter ratio of these is considerably smaller than the depth diameter ratio of simple craters. And as you go, this is, by the way, this is the Great Copernicus crater that's about 96 kilometers across from one side of the crater to the other. And it, again, all four of these are lunar craters. They formed on the moon. Now, when you get to even larger craters, such as the Schrodinger Basin here, this is about 320 or so kilometers in diameter from the outer ring to the opposite side. And you see it doesn't have a central peak any longer here. It's got a peak ring. So these are double ring basins or peak ring basins. And when you go even to larger craters, you go into the realm of multi-ring basins. And you can see here, this is the Great Orientale Basin. It's about 1,000 kilometers across here, about the size of Texas. And it's filled in the middle with a little bit of lava that occurred sometime after it formed. But these rings, these concentric rings, are one of the controversial aspects of crater morphology. It's also an aspect that I won't deal with tonight. I've got my hands full talking about a number of other things that we need to get through here. So how do craters form? Well, the simple crater is pretty obviously, and this is quite an old diagram, and I'm going to argue later in the talk about why it's wrong. But you can see that you have fractured target material here underneath the crater itself. The crater is partially filled, oftentimes, with debris or melted material that form due to the high pressures that accompany the impact event itself. And on the flanks of the crater is a deposit of the debris that was blasted out of the crater itself. So that's a simple crater. Now, the complex crater, the peak ring, the central peak and the multi-ring basins are thought to form in a similar way, but let's just look at the central peak example here. Something is causing the rocks that were originally well down below the zone of excavation in the crater to be uplifted. And we thought for many, many years that it was a rebound effect, that there was enough elastic energy stored in the target beneath the crater itself to where the central plug of material actually bounced back up, much like a water droplet, if you've ever seen those examples where when you drop a pebble into the water, you get a little blip of material coming up. It obviously has an influence due to elastic energy, but elastic energy itself is not enough. And so we've been struggling for the last decade or so to try to understand exactly what is causing this, but it's likely that it is strongly influenced by gravity. In other words, as the excavation zone collapses, then there is an inward and downward faulting that tends to drive this material down because it's gravitationally driven down, and just the accommodation of all this material down in here forces this material up. And that's a possibility as well, but I don't want to be dishonest with you about anything in these presentations. It's still very controversial, and I think there's plenty of room for students to make their contributions in the future on issues such as this. Okay. I'm not going to talk much about Mars, and I'm not going to talk much about Mercury because while I do have an active project that involves Mars and the Moon, and it focuses on the Zunil crater on Mars, I really haven't done very much work on Mercury, but I did want to show you this slide to give you an impression of why craters themselves are quite useful. You can see that this is a fault scarp here. It's called Belgica rupes. It's on Mercury. It's almost 1,000 kilometers in length here. And you can see that there are a number of craters that have either been deformed so that the scarp runs through the crater, or have been superposed on the crater. And so you can get an idea, if you can understand the number and size distribution of the craters themselves, you can get an idea of the relative age of this kind of deformation. The other thing that this doesn't show so well, but we can look at this little crater right here and understand it, is if there were any transverse motion, that is motion that moves side to side rather than up and down, it's going like this, then the crater rim there, because these are circular features, that crater rim would be offset on one side of the crater, or on one side of the scarp itself. And we don't see that, so we know that the style of deformation on that scarp is purely up and down. It's a normal fault. Okay. So those are a couple of really important uses of craters themselves. Now, I'm really interested in this crater Zunil because we've had this controversy for a long time. You can see that the ejecta from Zunil up here has these sort of distal or ridges, or they look like flow-like features. They're lobate scarps, and yet I'm getting ahead of myself. We've seen these on a number of craters on Mars, and there's one camp, and it's the largest portion of the community actually, that believe that what is causing these is subsurface water in the form of ice that is incorporated in the debris, and it, rather than sort of taking a ballistic trajectory outside beyond the crater, it flows, and these are sort of deceleration lobes right here. Now the alternate view is that there's something in the Venus atmosphere. The atmosphere is actually incorporated in the impact process itself, and these gases, these atmospheric gases, are causing these lobate ejecta characteristics. The nice thing about Zunil, however, is that the northern side of Zunil shows these lobate scars, but the southern side of Zunil shows normal ballistic ejecta. And so we have proven, at least in one case, that it has to be subsurface water. It cannot be atmosphere, because the atmosphere is going to affect the whole crater. But we know from other images of Zunil that down here, the inner wall of this crater has these layered look, much like the lava flows that we see on the moon, on the Mare surface of the moon. But on the northern side, these are all sediments that have been highly dissected by water. And so there's a target heterogeneity that runs approximately like this, so that there's a sedimentary cover right here, probably underneath which is volcanic rocks, but these volcanics are right at the surface here. So when you impacted this, you produced ballistic ejecta on this side and lobate ejecta on that side. And that's all I'll say about Mars. Most of what I've been doing in the last couple of years involves analysis of very high resolution imagery and topography that we now have for the lunar surface, thanks to the Lunar Reconnaissance Orbiter. And so in a couple of years ago, I was able to combine high resolution imagery and high resolution topography for something like 21 or 22 craters that are sitting on these very flat-lying lava plains that fill these giant basins on the surface of the moon. If you were here for Paul Spudis's talk last month or whenever it was, he must have talked at great length about these Mare basins. And the reason I chose the Mare basins is because it's easier for me to reliably constrain the location of the pre-impact surface. So once I was able to do that, I could see that these lava rocks, see these layers here, are indicative of the lava flows that have filled this part of the Mare Basin. And they go right up to almost the top of, right up to the rim crest. You can see them way up here. And so, unlike the previous interpretation of what the rim consists of, I showed that the rim is actually about 80 to 90% is just uplifted target rocks. They have been uplifted by the flow field that when the projectile hits the surface, it drives material down and out like this. And because if you push material down in this direction, it causes material to go up in this direction. And so this has pretty significant consequences for understanding cratering mechanics and energy partitioning in the impact event, but it has even more profound consequences for interpreting the Apollo samples, where they were originally located, because most of the rocks that we have now in our Apollo sample collection were materials that were collected that were not in situ. They were not sitting in competent rock that you could take a piece of and you knew exactly where that rock came from. They were debris that has been broken up and redeposited from giant impact basins that are 3.8 billion years old. And so this helps us understand where these rocks may have come from. And then the final thing is that if you have less material excavated, then the excavation zone itself has to be smaller. That portion of the original crater that is blasted outside the crater is called the excavation zone. So this material down in here, it never sees the light of day. It's pushed down and out and sometimes injected into the walls of the crater. And so that has a very important consequence for understanding how deep a crater actually excavates. And for these large basins, such as the South Pole Aitken Basin on the moon, we've had this dilemma about the typical excavation depth that you would expect from the South Pole Aitken Basin would be something on the order of 150 kilometers. In other words, if conventional wisdom held, then the South Pole Aitken Basin should be distributing mantle material all around it, probably of enriched in olivine. We don't see any olivine outside the basin itself, but with this revised view of excavation depth, the South Pole Aitken Basin would have only excavated about 50 kilometers, which is about the depth to the lower crust. And that's not mantle, or not olivine rich. So it seems to satisfy that problem. But again, because I'm brutally honest, as I always am, there needs to be a lot more work done here to really prove this or test it and refine it. All right, let me turn to the terrestrial cratering record now. I've had tremendous opportunities. I've visited every continent seen on this map, every continent on the planet except the one that's off to the south here. And every opportunity I get to go here is around Christmas time, and I'm sorry, that's just never going to happen. But when I was a postdoc in Canada, I studied a number of these craters up here. And this little crater right here is the Marquet Dome. John Gibson and myself discovered that in the, I guess it was the late 80s. And like I say, I've been all over Australia with Gene Shoemaker. It's been a blast. One of the first people to go into Mongolia after Kevin Burke and I, after normalization of relations there, and looked for impact craters all over China and Mongolia. It was a fantastic trip. So what I want to leave you with here is that this is there are very few impact craters that you can find on the Earth, and the reason is the Earth has a very active, hydrospherically driven weathering regime. So craters get eroded away very fast, they get infilled very fast, and then on top of that, we have this active plate tectonics regime that if a crater forms on the basaltic seafloor, then its fate is to be subducted, and it will be subducted within about 200 million years, and when we're talking geological timescales, that's fairly small. So you can see that there's sort of a non-random distribution of cratering. There's a lot of craters in North America because we have a very active program to find craters either through geophysical techniques, drilling techniques, field studies in Canada. These are old terrains up here, the Canadian Shield, other shield areas such as the Finno-Scandian Shield and the Australian Shield also have retained a lot of craters. When you have sort of rainforest areas, it really takes a lot to find an impact crater there, and so there are very few that have been discovered there. This is, and the one thing about craters on the Earth is that every one of them has been modified. I mean, any crater above about a kilometer has been affected pretty substantially. One of the freshest is the Barringer crater, or meteor crater in Arizona. It's about a kilometer across. You can see that it's not circular, it's square, and that's because the cratering event took advantage of a orthogonal set of weaknesses, lineaments that cut like this, and so because the faults were there, it was easier to excavate in these directions than in other directions. So it has sort of a square shape. This is the Elgin crater in Siberia. I was involved in some lake drilling to find the central peak there and to understand the sediments. These crater lakes form a really great opportunity for looking at the ancient history of the Earth. The sediments retain a very complete record of the climate history of the Earth, and this happens to be a very important one because there's not very much other climate history evidence in that part of Russia. It's about 26 kilometers in diameter. This is Manicouagan, and in Quebec, you can see the Manicouagan Reservoir here. It was carved out by Wisconsin age glaciation. It's not really the crater rim. The crater rim is out here. Crater rim has been reconstructed to be about 100 kilometers in diameter. That little thing there is the tail of the shuttle. This is a shuttle image here, and on the inside is highly shocked and melted rocks. And then, of course, the Chicxulub crater I was involved in. I was the principal investigator in the 2000 drilling project to drill down into Chicxulub, and this gravity anomaly map here that you see in perspective view was one of the items that we had in our science paper that showed the first evidence of Chicxulub being a multi-ring basin of about 300 kilometers in diameter. Another one that I spent quite a bit of my career going to is Slate Islands, just offshore of the northern shore of Lake Superior, and you can see one of the wonderful opportunities, advantages of terrestrial rocks, or terrestrial craters rather, is that most of the crater has been wiped away. All of the crater in this case has been wiped away, and you're looking underneath the crater and you're getting a glimpse of how the rocks have been amalgamated, giant blocks, some of them the size of a football field or larger, but they've been welded together by impact melt and fragmental breccias. So it really gives us a clear understanding of how the rocks behave underneath and on the margins of the impact event itself. Again, this is Houghton Crater in the Canadian archipelago. This is a Landsat image, and I've tried to make it as true to color as possible. And you can see the sort of blue-gray units that run right in here. These are remnants of the actual breccia that fills the crater itself. So this is a real crater, but it doesn't retain a lot of topography, but it still retains some topography. And you can see some darker areas right in here and right up in here. Those are rocks that have been uplifted, much like the rocks in Copernicus has. So it's a central peak crater. And then if you look, and it's hard for me to see, but I think right in this area are rocks that are slightly different in color. And those are lake beds that that were deposited right after the crater formed. It filled up with water. Sediments occurred over several tens of thousands of years, and those lake beds have been partially retained in the crater ever since, even though this crater has experienced significant glaciation. So here's the topography of the crater itself, and these purplish ones are very low, and there's about 350 meters of relief out to the rim, if you will, what remains of the rim at about a radius of about 12 or 13 kilometers. And then we've done a lot of mapping out here. The main target is carbonate, Allen Bay carbonate. Here are those rocks that have been uplifted, the Eleanor River rocks, and then you can see the Houghton Formation or the lake beds that have been retained here. And these lake beds are extremely important because they tell us the age of the cratering event itself. The nice thing about, again, about the terrestrial record is that we can subject these craters to geophysical techniques such as reflection seismic. And with that information, we can take a surface view like this and the stratigraphy that we have here and the seismic data, and we can understand the workings of the crater in 3 dimensions. So, and that's all I've done here. This is the seismic reflection data here, and I've incorporated the stratigraphic interpretations of each of these reflecting horizons. And then I've had to fudge a little bit. There's no reflection data over here, but I've just used this to carry it over here and make it consistent with the exposures at the surface. And so you can see in 3D what a terrestrial crater of about 25 kilometers in diameter actually looks like. Why is this important? It's a good question. You know, I always have to think about why things are important nowadays. When I first started out, it wasn't like that. The importance was you were satisfying your curiosity, right? You know, I mean, it's like that was the fun part. And you can still do that, but you're doing it at taxpayers' expense. So you better be thinking about why it's important, you know. So anyway, so why it is important is because it tells us the geometry of the excavation zone itself. And I don't want to get too deeply into this, but there were, prior to my work at Houghton, there was a couple of hypotheses that the excavation zone was either 10 kilometers in diameter, or actually 5 kilometers in radius, or 15 kilometers in diameter, equivalent to 7.5 kilometers in radius. And there was a model that everybody used back then called the Z model that dictated how material flowed outside and was ejected on the flanks of the crater. That's the Z model itself. And so that we had 2 different models. Now, my work showed that the stratigraphy at the top, the exposures of rocks on the surface of Houghton were inconsistent with either one of these. In fact, what we have to have is a central narrow zone of deep excavation that actually gets into crystalline rock down here. We see that at the surface, but retains the Calvert Bluff here and the shallower target rocks up here. Because if you had excavation that followed this curve, then all of these rocks would have been removed. But we see that the green rocks have been retained. We see outcrops of them all the way to here. Same thing's true with here. This one would have removed all of these rocks right here. And so we wouldn't have any outcrops that are at this distance from the crater center. So that was kind of a nifty conclusion. Now, I want to turn the attention to Venus, because I was asked to give principally a Venus presentation. And I know a little bit about Venus. No one knows very much about Venus. It's one of the most poorly understood planets in the solar system. We have better data for many of the Galilean satellites than we have for Venus. And the reason is that the atmosphere of Venus is opaque. It's very dense. It's very it's filled with sulfuric acid droplets that you can't see through using normal visible technologies. So you have to use radar. And radar is one of those mind-numbingly boring things that I've spent most of my life trying to understand. So what we see here is a Pioneer Venus image that it had a UV instrument, ultraviolet instrument. And unlike that first image that I showed you where it was just purely smooth blue, you can actually begin to see some structure in the atmosphere using ultraviolet. But you still can't see through the clouds. And the great thing that Magellan back in 1990 did for us was it exposed the surface at reasonably high resolution. And so you can see these bright equatorial highlands here. This is Aphrodite Terra, and giant circular features that are not impact craters. Unfortunately, it'd be a much more intriguing planet if those were impact craters. But that's what I want to finish up the presentation with. How am I doing on time? I was a professor for a long time, so I'm very long-winded. Okay, so I've got a little bit of time. All right. We searched throughout the 3 or 4 years of Magellan's, actually it was quite a bit longer than that, but after 3 or 4 years you get tired of it, you know, and go and do something else. But after we had one global map of Venus, then we discovered almost 1,000 impact craters. But we didn't see any impact craters that were the large basin-forming impacts that you see on Mercury or on the Moon in particular, or even remaining on Mars. There was nothing like that. So we knew immediately that the surface of Venus had to be quite young. It had to be younger than about 3.8 billion years old, right? And then when you look at this, you stare at it until you're cross-eyed, you realize that the distribution of impact craters is quasi-random. It's almost as if you just fired a shotgun blast at the planet and the pellets were distributed in a random way. That's an interesting thing in itself because it's telling us that, at least at this resolution that we have now, we can't discriminate one surface unit, the age of one surface unit from another. If there was a very young surface unit on Venus that was something of this size or larger, then and it was very young, then we would expect to have many fewer craters on it because craters kind of come in a metronomic sort of way. It's sort of a constant rain of impact events. And so the younger the surface, the fewer the craters. But we don't see that. We see a sort of random distribution that's everywhere pretty much the same. So that tells us something important about how this planet was resurfaced. The largest crater is the Meade Basin. It's about 280 kilometers in diameter. So it's about the same size as Chicxulub is to Chicxulub's outer rim. The smallest craters, however, are in the range of 1 or 2 kilometers in diameter, but they're always broken up. You never see a pure, simple crater on Venus, and the reason is the atmosphere is so dense that when these projectiles come in, they are impacting into the atmosphere itself, and they're beginning to be broken up and slowed down. And so the feature that is formed on the surface has already been affected by the transit through the atmosphere. All right? And so we are missing a huge number of craters that you would have on a planet that hasn't got an atmosphere. And this tail off, which is the distribution, the size frequency distribution of craters on Venus, you can see that it goes up almost in a straight line till you get to about 30 or 25 kilometers in diameter. Then it starts to be affected dramatically, and by the time you get in the size range of a couple of kilometers, there's virtually none. And all of these diagonal lines are telling you is that if you had a surface of a given age, and this is 4 billion years old, this is a billion, 100 million, 10 million, a million, and 100,000, this is the distribution of craters that you would expect to find. So the atmosphere is playing a tremendous role in removing impact events and probably affecting the nature of the cratering event itself, even in this range. So this is where we get it. We're going to do a little exercise in logarithms here, because I know everybody's happy about that, right? Yeah. And the reason is because the typical way that we express the relationship between the diameter of a crater and the depth of a crater is through these log-log plots, they're called. And a log-log plot, unlike a linear plot, if you just look at the distance between the 1 and the 10, it's the same distance as between the 10 and the 100. So the length of any given area is just an order of magnitude, or a factor of 10 rather than a factor of 1. Same thing's true on the depth scale. And the reason we do this is because when you have power laws, which are of this form here, where depth is equal to some constant of proportionality times the diameter raised to some exponent, then these power laws form straight lines in a log-log plot. And so you see here on the right, this is work that Richard Pike did, great guy, tremendous guy, back in the early 70s, that showed that these relationships between the rim diameter, as it increases, this is the way the depth is dependent on diameter. And you can see that it goes out to a certain point, and then there's a big kink, and it shallows out. These are the simple craters, and they have a depth-diameter ratio that's really linear. It's approximately, the depth is approximately equal to 20% of the diameter. Almost everywhere in the solar system that's true. But when you get out to this junction here that is called the simple to complex transition zone, then the craters become complex craters, and they take on a different formula, a different equation between the depth and the diameter. So these, all I've plotted here are the regression lines for the data sets that have been collected for the Moon, Mercury, and Mars. Down here is the best attempt to see to get a regression line for the Earth, although it's very fuzzy. It should be very wide, actually. And then Venus was thought, because it's very hot and it has a thick atmosphere, that Venus craters should be very, very shallow. They should be shallower than those on the Earth. So this piqued my interest, and when Magellan began to collect data, I started to think about, well, how can we test this? And a way that Kurt Klaus and I actually, and he's in the audience, he was, a long, long time ago, he was a graduate student of mine. And so we looked at this, and we recognized, as did others, that because radar is a side-looking technology, where in this instance it's looking off to the left and it's looking in this direction, it's looking toward the east, that it illuminates the surface with radar waves that it is projecting, and then those radar waves are bounced back to the instrument itself. So we we noticed, along with others, that there was a systematic distortion on the side of the crater that was close to the radar. It had a rim zone from the rim crest to the floor of the crater that was very wide compared to the rim on the other side of the crater. And because of this slant range distortion, we could use a little bit of trig, and we could actually back out the depth of from the rim crest to the floor of the crater, which is exactly what we needed. And we did this with 90-something impact craters because there's huge errors associated with this. And so you have to beat those errors down using a large sample size. And so that was the intent of our research. And so this is what Venus looked like before we did that. And then here's the data that we got. Unlike previous predictions and estimates of what Venus craters look like, we found them to be quite deep. There's a lot of scatter in this data, but that's the regression line. Okay. So this is incontrovertible evidence. And it has been shown more recently through stereo analysis of the Magellan data that these data have held up. So pretty interesting conclusion there. But that's only part of it. When we begin to look at different morphologies on Venus, Jerry Schauber, Bob Strom, a bunch of people had noticed that there were very, very few craters on Venus that seemed to be involved in the resurfacing event itself, at least from a volcanic standpoint. Now, this is the Alcott crater. It's about 60 kilometers in diameter here, rim to rim. And you can see the northern part of the crater has been removed completely. It's been covered by lavas that have come down from the flanks of a giant volcano. And you can actually even see a little levied channel here where that's a lava source there, and it's cracked through the ejected deposit itself. Only about 4% of all the craters on Venus show evidence of being involved in the volcanic resurfacing of the planet. That's really significant because the fewer craters that show evidence of being modified by volcanism, the shorter the resurfacing event itself. So the duration of all that volcanic activity had to be very, very short. So if only 4% of the craters are volcanically modified, then the resurfacing event that occurred about 800 million years ago only lasted 32 million years. So the whole planet was resurfaced to kilometers deep, all the way globally resurfaced in 32 million years. That would make it by far the most volcanically active planet in the inner solar system and the second most volcanically active planet or satellite in the solar system itself, only exceeded by Io. Okay. So, is this the situation? Well, we noticed that some of the craters had very bright blocky floors, such as the Aurelia crater, which is about 30 kilometers in rim diameter here, and other craters, such as the crater Adams here, which is about 60 kilometers in diameter, had very dark floors. And the dark floors look very much like the surrounding lava plains. And so we began to look at the distinction between dark floor craters and bright floor craters. Now, the other part of the puzzle is that the vast majority of these craters that have bright floors also have this very interesting halo around it that you can see here and the Adavar crater, which is about 30 kilometers. This is the youngest crater on the surface of Venus. It is probably not more than about 100,000 years old. Okay? So it's unique. There is none other that has a jet of material that spews out looks like the head of a rotting guppy, you know. But what you see here is the apex of a parabola of material that opens to the west and goes for hundreds of kilometers. Speaking of guppies, if we look at an emissivity map, this is an emissivity map. Here's the scale. So there's about 3,000 kilometers on this right here. So, you know, you're dealing with a better part of 8 or so thousand kilometers across here. And if you begin to stare at this enough, by the way, this is an emissivity map. So, how am I going to do this? Emissivity. It's one of those theoretical things that drive people nuts. Emissivity is just the complement of reflectivity. It's the amount of noise or energy that is released by an object because it is at a certain temperature. Okay, that's all you got to think about. Now, the way we look at it is that emissivity is the complement of reflectivity. So these dark areas right here are actually very, very bright in radar reflectivity. Okay, so but when you look at it, you begin to see these parabolas all over the place. I mean, it looks like a school of angelfish in what would be a terribly maintained aquarium. Right? And these are the youngest craters on Venus because these, and I'll explain why these are produced, but these are very temporary features. They are erased very quickly on time scales of tens of millions of years, all right? Because we only have a handful of these, and there are 900 and something craters, so you can get an estimate of about how long it takes just by understanding that ratio. So how are they formed? Well, what we think happens and what the evidence leads us toward is that you have an impact event on the surface of the planet and it blasts material in all different directions, but when it goes up to about 45 to 65 kilometers above the surface, it becomes entrained in these easterly winds. And rather than being deposited to the east, the winds drive this stuff to the west. So you get these parabolic shaped features here. And there's if you really look carefully, you can see them. There's probably 8 or 10 of them in here. Okay, but quite amazing features, and all due to atmospheric entrainment of ejecta and redeposition downstream. If you ever want to, you know, we never think about Venus having life. It's extremely hot. It's 460 degrees at the surface. It's hotter than Mercury is on the sunlit side by about 40 degrees C. And it's all due to this super greenhouse that it has. And we're never going to put astronauts at never. Don't ever say never. But, you know, we're not going to see it. I don't care how young you are. You know, it's not going to see it. But it still has some importance with regard to life, and that is because at about 65 kilometers above the surface temperature is about what it is on the Earth. Surface pressure, or atmospheric pressure, is about what it is on the Earth. And there are all kinds of reactive species here because of the sulfuric acid, and there's plenty of water. So if you were to look for life, you would expect it to be some sort of microbial infestation, as all life is, that's located in sulfuric acid clouds here. So I think that's really cool. I mean, that's a good reason to dip into the atmosphere as far as I'm concerned, but my curiosity. So, but anyway, so I looked at, Kurt and I actually looked at craters that had these parabolic deposits, and they plotted up here. And then we looked at craters that had these dark floors, and they plotted down here, which leads us to postulate, that's the honest word for it, but I think I was a little bit more direct in my paper. I think we said conclude, that there's, let's see, let me go down here, that these dark floor craters are actually indicative of craters that have been involved in the resurfacing event itself. They have been affected by the resurfacing event, not from the outside, not by lavas coming in over the rim, but by the fact that the crater floor is deeper than the surrounding surface and so has been invaded from underneath by lava. So, why is this important? Well, if the surface is about 800 million years old, and we only have about 4% of the craters on Venus have been modified, then I think, as I said before, it would only, the resurfacing event, the global resurfacing event, would have lasted only about 30 or so million years. And that would make Venus unique in the inner solar system. It would be literally a global catastrophe. But if all the dark floor craters are indicative of having been involved in the resurfacing event itself, and there are about 60% of those in the cratering record, then you've extended that event, the duration of that event, to something like 500 million years. So it's not that much different from the situation that we have on Earth. And so you could have gradual, piecewise, ongoing resurfacing, rates similar to what we see on the Earth. But as I'll point out in the last slide I'll have in just a minute, without plate recycling. Venus is clearly a volcanic planet. There's no question about it. They have these large volcanoes like Sapus Mons and in the background Mons. You can see lava flows extending for hundreds of kilometers from these edifices here. You have these very interesting coronae. This is a coronae called Ibn Kuvak. It's about 100 kilometers in diameter. You can see tectonic features, linear tectonic features here, but you can also see places where lavas have filled a moat that goes around like this, and a variety of other lava features here. So these are some sort of volcanotectonic feature, probably a hot spot or a frustrated volcano. You had a hot spot that kind of came up, pushed the surface of the planet up a little bit, spewed a little bit of lava, but it didn't have enough energy, enough heat in it to really to create a volcano, and so it collapsed again. That's the working hypothesis anyway. And then you have these very interesting features called tessera. This is Alpha Regio here. It's about 1,300 kilometers in diameter, and it just looks to be crumpled up. You're hard-pressed to really see anything. There are a few impact craters on here, but they, it's really hard to see. But it looks like along the margins, the lava plains have kind of washed up on the margins and are kind of covering the edges. And you can even see some lava domes out here, and quite a bit of lava stratigraphy here, some smooth lavas, some not so smooth lavas there. and there's another corona. So there's no question that Venus is a volcanic planet. What I think Magellan has told us without very much room for doubt is that Venus doesn't have any global scale plate tectonics. It has a very buoyant, in order to have plate tectonics, you need to have two things. You need to have a lithosphere, which is the topmost structural part of the planet, that is very much denser than the underlying mantle. And you also need some sort of lubrication here so that this material slides out here, and then when it, in a subduction zone, it's actually driven down into, that's not exactly right, but this actually pulls the plate along. And it's finally digested back into the mantle when it gets down to 700 or 800 kilometers below the surface. Now, it's really interesting for maintaining habitability on this planet. There are a number of things that we're blessed to have on this planet, and the reason that we're here. One of them is a magnetosphere. Keeps a lot of the high energy particles from hitting the surface and doing a lot of damage, oxidation, and we'd have such a high radiation environment that life wouldn't be able to survive. But the other thing is plate tectonics, because when you put water in the atmosphere, and there is a lot of water in the atmosphere, it photodisassociates. The photons coming from the sun break the water molecules up into hydrogen and oxygen. Hydrogen is a very, very light element, so it bounces out into space, and it's gone forever. Once you lose an atom of hydrogen, you don't ever get it back. And so the problem with Venus is that it didn't have this plate tectonics, and so whatever water it had at the surface has been removed through this photodisassociation and lost forever. The oxygen has then incorporated into and oxidized the surface materials, producing that ugly rusty color that I've shown you throughout this slide sequence. So the reason that we are here today, 4.5 billion years from the time this planet formed, is because the biggest reservoir of water on this planet is not the oceans, it's the mantle. Because when you subduct material, you subduct a lot of water back in, and so it's constantly, the mantle's constantly being replenished with water, and if it's in the mantle, it's not free to be photodisassociated, put in the atmosphere, and driven away with time. So this is one of the things that has allowed the Earth to maintain a habitable environment for so long. All right. So whether or not we had catastrophic resurfacing is going to be up to the next Venus mission, hopefully. At least at some time in the future, we need a high-resolution radar mission. But I think from my standpoint, the reason I've been and continue to be so intrigued by this planet was I would like to know if Venus ever had an Earth-like environment. Early in the solar system, if you believe stellar evolution theory, the sun was a lot fainter than it is now. And so Mars would have been super frozen, Earth would have been a snowball, but Venus would have been a perfect environment early in the history of the solar system. So life may have formed there, possibly. Are there any remnants of that epoch if it actually occurred? That I think that in itself is justification enough for a radar mission, a new radar mission to Venus, to see if we can find surface evidence for any vestiges of that earlier habitable environment that's left. And another question is, what caused the shift to this hostile environment that we see today? And then finally, bringing it back to our planet, is what does this tell us about the fate of habitability on this planet? So I'll be happy to take questions. Thank you very much for your attention, and let's talk about it.
Okay, we'll come up and down the aisle if you have a question.
Yeah, Larry.
Yeah, and you use mic, please.
Your discussion about how the atmosphere of Venus affected the distribution of the impact debris and made those parabola-shaped markings makes me wonder what effects Earth's atmosphere might have on the distribution of impact debris on this planet. We don't have as thick an atmosphere as Venus, but we do have an atmosphere.
That's right, yeah. Well, it protects us a little bit, doesn't it? I mean, we see objects that would have been crater producers, such as Tunguska, in 1908, that were broken up by the atmosphere, and the vast majority of energy was dissipated in the atmosphere rather than producing an impact crater that could have been somewhat devastating if it occurred over a city, something like that. So the atmosphere provides a shielding. As far as what effect the atmosphere would have on the subsequent distribution of ejecta after a cratering event occurs, I'm not sure there's been a lot of research in that. I think David Cratering probably has written a paper or two on some theories about how Meteor Crater, Barringer Crater in Arizona may have been affected by the atmosphere, or yeah. But I don't know. I'm, beyond my limited abilities. Alan. Oh, there's somebody else. Okay. What's the matter?
It's not working here, but partly in answer to his question, you can see something of how atmosphere might have affected a meteor impact stuff by how it affects how is that going now? How it affects a volcano eruptions, like the Mount St. Helens.
Right. Well, okay.
So, this ash cloud went way up from Mount St. Helens, and it drifted eastward, not westward. So our atmosphere is going to have an effect on that.
Yeah, and Chicxulub had the same event itself. It had, the ballistic ejecta that was distributed broadly, but it also had that fireball that came up and then collapsed back down and left all these beautiful glass beads in the Caribbean and Gulf of Mexico.
But I do have a question also.
Okay.
Talked about volcanoes and all over Venus. Are any of them active now?
I think there's good evidence that they are, and you know that. That was a softball. But, yeah.
Tell us why.
Yeah. Well, Venus Express, which was a European mission that I think it's just concluded last year, I believe. It had an IR emissivity mapping instrument that was designed to look at the atmosphere, but it found that there were a couple of windows where IR at about 1 micron, a little shallower than 1 micron, there's a window that IR can actually see through to the surface, and it measured some anomalies that are highly suggestive of active volcanic activity, or at least very, very hot surfaces, much, much hotter than than 460 degrees. So yeah, it looks like there might be some active volcanism. Yes, yes, sir.
Given that a long time ago, Venus had an atmosphere and the Earth continues to have an atmosphere, when there's a cratering event, is there any likelihood that the upward flow of material at the moment of impact may create a decrease in the atmospheric pressure that sucks a lot of this stuff up and then it falls down?
Yeah, that's a good point. And in fact, even on the Earth, for an object that's in the range of 10 kilometers or better, there's actually a vacuum that's produced behind the projectile. When it comes through, it just pushes the atmosphere away, and so you're left with a vacuum for a short period of time, then it slams shut. So any material that is blasted up in the intervening time is then shot out of the atmosphere. So we've probably lost a lot of material from Chicxulub, and the same thing could have happened on Venus. Yeah, that's a good question.
All right, let's thank our speaker one more time. You have a chance to chat with them out in the lobby.
Thank you. Yeah.
Thank you all again for coming this evening. And February 2nd with Dr. Georgiana Kramer. She's going to talk about lunar swirls, which are really interesting, not squirrels, which she will say, but swirls, a very interesting phenomenon. She'll be telling us more about that. So thank you and good night. If you're online watching us, good night. Thanks for joining us.